Okay, everybody, welcome to your first homework video for unit number 5. Today in class, we talked about kind of a review of how to simplify square roots and cube roots, whether it be just numbers inside the radical or numbers with variables with exponents. So the next logical step in this radical journey is to talk about operations. How are we going to put these things all together? We can treat radicals just exactly the same way that we treat any other variable, x's, y's, a's, b's, c's, whatever your variable of choice is. We treat radicals the same way. So we can perform operations on radicals just like we would terms with coefficients and variables. So when it comes to the different operations, we've got 4 of them: addition, subtraction, multiplication, and division. And addition and subtraction have the same rules, just like adding and subtracting terms with variables have the same rules. Because radicals act just like variables, when you're adding and subtracting, you can only combine, everybody say it with me because you know what I'm about to write down, like terms. Have you gotten sick of seeing like terms yet? We can only combine like terms. So if I'm given an addition problem, like 2 square root 5 plus square root 80, these are not like terms. We cannot add them together, but that's not to say they can't become like terms. When we're doing addition and subtraction, our first step is to always simplify any radicals that we can simplify. So 2 root 5, we can't do anything about that. 5 is a prime number. It has no factors other than 5 and 1, so it cannot be simplified beyond just 5. But 80 is pretty big. There's probably a perfect square that we can divide evenly into 80. In fact, it's square root of 16. And then square root 5 is the other factor. 16 times 5 is 80. 16 we know will square out to 4. So the square root of 80 will simplify to 4 square root 5. And when I could not combine 2 square root 5 plus 80, I can combine 2 square root 5 plus 4 square root 5. Sorry guys, still working on that whole bronchitis thing. So 2 square root 5 plus 4 square root 5. Just like matching variables, these are now like terms. Root 5, square root, perfect. I can add these two things together. And just like if I had 2x plus 4x, I would say, well, if I've got 2x's and 4x's, put them together in the same pile, I've got 6x's. I add the coefficients. I do the same thing with radicals. Okay, I combine the like terms according to the given operation. If the numbers or the variables with exponents inside the house match exactly, then we perform the indicated operation on the outside numbers. Consider those the coefficients, consider the radicals the variables. So in this case, 2 square root 5 plus 4 square root 5, just like 2x plus 4x, I'm adding the coefficients together. So I'm adding the 2 plus the 4. My answer is 6 square root 5 because 2 plus 4 equals 6. And it works in the opposite way with subtraction as well. But you must have like terms. You cannot say, oh, 2 square root 5 plus 80, well, that's 2 plus the square root of 85. No, it doesn't work that way. They've got to be in the same format. They've got to be like terms. Okay? I don't want to beat a dead horse with this. I'm not going to give you a million examples in these notes because I think we're at the point in our journey together where we understand like terms mean identically matching terms. If they're not the same thing inside the house, see if you can simplify to get them to be the same thing inside the house. And if you can, great, add the outside numbers. If you can't, then you leave it as it is, just like we would with any other polynomial. Okay, now multiplication. We're going to keep this video short and sweet because it's the weekend, and I know you guys are not that thrilled about having homework on the weekend. Multiplication is a different story. There are not the same rules as there are with addition and subtraction. There are rules. It's not a free-for-all. But we don't have to have anything that matches. We just go for it. When we're multiplying, we just throw everything together. we can simplify first, or you can simplify after you multiply. But you know, when you multiply two numbers together, you're going to get a bigger number as the answer. And the bigger the number, the more difficult it can be to simplify. So I always suggest simplifying first and then doing your multiplying. So 2 square root 5, we already established cannot simplify. The square root of 12, we talked about this one in class today, and this is an easy one. You guys should have this like memorized, no big deal. We know that the square root of 12 can, in fact, simplify because we can break this down to the square root of 4 times the square root of 3. Square root of 4 squares out to 2, and the square root of 3 stays inside. So square root 12 simplifies to 2 square root 3. We've got our simplified radicals written here, 2 square root 5 times 2 square root 3. So here comes the rule, and the rule is very simple. Outies and outies, and innies and innies. Never do the two cross the threshold of the house. You multiply the numbers outside the radical together and keep them outside. And you multiply the numbers inside the radical together and keep them inside. So in this case, if we're working with 2 square root 5 times 2 square root 3, then the 2's that are outside get multiplied together. These numbers were outside the radical, so the 4 will stay outside. And then the numbers inside, the 5 and the 3, they get multiplied together. These numbers were inside the radical, so 15 will stay inside. The only exception to never crossing the threshold is if once you do that first round of multiplying, outies and outies, innies and innies, if your number inside the radical now can be simplified, then you can move things back outside. But in our case here with 4 square root 15, we can't simplify that. 15 has two different sets of factors, 1 and 15, and 5 and 3. And there's no matching pair of identical factors in there anywhere. So 15 has no square root. We're going to leave it exactly where it is. 4 square root 15 is our product of 2 square root 5 times 2 square root 3. Or our initial offering of 2 square root 5 times the square root of 12. It's all the same. So here's a couple other examples for multiplication problems that you might see. And just at first glance, this should not be that crazy. If you replaced all of these radicals with variables, then you would look at this and you would say, oh, I know exactly what to do here. This is a monomial times a binomial. I'm just going to distribute. And oh, I know exactly what to do here. This is 2 binomials. I'm going to FOIL. And that's what we're going to do. Let me switch this up. We're really going to squeeze it in here. But we're going to multiply just as we normally would. The only exception is keeping the outies together and keeping the innies together. So I don't have anything that I need to simplify here. I've made this one easy. We're going to multiply 2 square root 5 times the square root of 3, and then 2 square root 5 times 3 times square root of 2. So if I'm multiplying, oh geez, it's been a long day, you guys, long couple of days. 2 square root 5 times square root 3. You know there's that invisible 1 outside, so 2 times 1 is 2. And 5 times 3 stays inside the house as 15. And now I've got 2 square root 5 times 3 square root 2. So outies, 2 times 3, well, that gives me 6. 5 times 2, that gives me 10. So I'm left with 2 square root 15 plus 6 square root 10. I can't simplify either of those. So this is my answer for the original problem of 2 square root 5 times square root 3 plus 3 square root 2. Now, when we get over to foiling, it takes a little bit more effort to keep yourself organized. You're still going to do your first terms, then your outside terms, then your inside terms, and then your last terms. But for each combination of those two terms, you have to do the outies and then the innies. So it just takes a little bit longer. It's a little bit more laborious, but no big deal. We're big kids. We can handle this. So the first thing is to check and see if there's anything that needs to be simplified, and there's not. We're going to do our first terms. 2 square root 5 times 6 square root 3. Our outies are 2 and 6. That's going to give us 12. And our innies are 5 and 3. That's going to give us 15. All right, then we're going to do outies. Ooh, and this is where it's going to get interesting. 2 square root 5 times negative square root 5. 2 times negative 1 is negative 2. Square root 5 times square root 5 is the square root of 25. We're going to come back and simplify that because we know that's a perfect square. Okay, now we're going to do our inside terms. So 1 square root 2 times 6 square root 3. 1 times 6 is 6. 2 times 3 is also 6. And then we're going to do our last terms. 1 times negative 1 is negative 1. 2 times 5 is square root 10. So we cannot simplify square root of 15, square root of 6, or square root of 10. Those are all going to stay the way they are. But square root of 25, well, that squares out to 5. And since I have a negative 2 already out here, that means I've got 5 times negative 2, which is going to give me negative 10. So I'm going to rewrite this as 12 square root 15 plus 6 square root 6 minus 1 square root 10 minus 10. And I always tend to stick the constant there on the end. Okay? That's multiplication. We'll do way more practice in class, but don't let something like this intimidate you. Multiplying radicals is no big deal. Just the outsides and then the insides. Keep them separate. Like boys and girls at summer camp. Keep them on opposite sides of the lake. I can make that joke because I was a camp counselor. Okay, so we did addition, subtraction, multiplication, and now we need to talk about division. I would be remiss not to talk about division. So the main thing that we have to remember with division involving radicals is that you cannot have an irrational denominator. Okay? You cannot have an irrational denominator, which means, and you know I just write denom for denominator because that's such a long word. So irrational denominator means that you cannot have any radicals in the bottom of a division problem, which is essentially a fraction. You can't have a division problem or a radical in the bottom of a fraction. So how do we fix that? There's two different ways to go about fixing this. Your first option is if there's just one radical in the denominator. So in order to, I can tell you how to fix it, but I want you to understand why we fix it this way. Okay? We must understand that squaring something is, we talked about this today, it's the inverse operation of square rooting it. So if we see something inside a radical, like the square root of x, we can make that radical disappear by raising it to the second power. Since the index here is 2, we know that because it's not written, then raising it to the second power will make the house crumble. It'll make it go away. It will rationalize that radical. So in order to square it, we have to multiply it by itself. Square root of x times square root of x. Well, that's the square root of x squared. I've got a square root and a second power. Okay, those two things do not compute. They dissolve each other, and now we are left with just the thing that was inside the house to begin with, and that is the x. So, long story short, in order to rationalize a denominator, you just multiply the denominator by itself. Let's look at 4 square root 3. In order to rationalize this denominator, all I have to do is multiply it by itself. But if I do that to the bottom, you know we got to do it to the top. So now we've got 4 times the square root of 3 divided by square root of 3 squared. And we know that the house is crumbled. It's like Superman and Kryptonite. The house is destroyed by squaring it. So we now have 4 square root 3 divided by 3. The other thing that you have to remember is that when you are dividing and radicals are involved, you can only reduce numbers or perform actual division on numbers when they are in the same format. So I could not divide the square root of 3 by 3 and all of a sudden say, oh, 3 divided by 3, well, that's 1. So the square root of 3 divided by 3 must be the square root of 1. No, they're not in the same format. We cannot divide them. If we could divide 4 by 3. That's not going to give me even division. It's just going to leave me with a fraction of 4/3. So this is my answer. 4 times the square root of 3 divided by 3. It's okay to have a radical up top. You can have a radical in the numerator of your division problem, but you cannot have a radical in the denominator. Let's look at one like this. 225 divided by 25. Well, what does 225 square root out to be? Is 225 a perfect square? The answer is yes. The square root is 15. Is 25 a perfect square? The answer is yes. The square root is 5. What's 15 divided by 5? Well, it's 3. That was easy. If both of these things are radicals and both of them happen to be perfect squares, that's a silver platter problem. That's no problem. You just simplify those square roots and then do the actual division if you can. What about 4 square root 12? How are we going to fix that? Well, we're going to multiply by itself in order to rationalize that denominator. That's going to give me 4 square root 12 divided by 12. Now we know that we can simplify the square root of 12. So what do we simplify that to? We simplify the square root of 12 to 2 square root 3, right? Square root of 12 is the square root of 4 times the square root of 3. This is 2. So we have 2 outside and 3 inside. Well, what happens when we already have a number waiting for us outside? We have to multiply the number that we're bringing out times the number that's already out there. So 2 times 4 is 8. That square root of 3 stays, and we have 12 in our denominator. The last thing we can do is we can reduce 8 12, can't we? How many times does 4 go into 8? Twice. How many times does 4 go into 12? 3 times. So my final answer for 4 divided by the square root of 12 is 2 square root 3 divided by 3. That one required a little more work, but hey, we can handle it, no big deal. Where things really get interesting is if there's an expression involving radicals in the denominator. So in order to fix this, we have to multiply the denominator and the numerator by the conjugate. I know you guys have heard me say this before. We're going to talk about it again. The conjugate is the same expression with opposite signs. And when you multiply something by its conjugate, something irrational by its conjugate, you wind up with a rational whole number in its place because of the power of math, the wonderful magic of multiplication. So, in this particular case, we have 2 divided by the square root of 7 plus the square root of 3. So we're going to multiply, I'm just going to rewrite this. Square root 7 plus square root 3. We are going to multiply by its conjugate. What is the conjugate of the square root of 7 plus the square root of 3? Square root of 7 minus the square root of 3. Square root of 7 minus the square root of 3. Okay, so we're going to set this up. I'm going to move this a little bit because I'm starting to write a little slanted. First, we'll do the denominator, and we basically have, first we're going to do the numerator, and we basically just have a distribution problem, right? We need to distribute the 2 into both of these terms. So we'll wind up with 2 square root 7 minus 2 square root 3. We cannot combine these terms. They are not the same. There is nothing that can be simplified. That's it. Now for my denominator, we're going to FOIL. I'm going to reserve this space for our actual answer, and I'm going to set up our FOIL problem here. So I don't know what kind of radical that was. The square root of 7 plus the square root of 3 times the square root of 7 minus the square root of 3. All right, here we go. So our first term, square root 7 times square root 7. Well, that's going to give us the square root of 49, which we know will square out to 7. Square root of 7 times the negative square root of 3 is going to give me negative square root of 21. Because remember, we don't have any coefficients outside, so we can skip the multiplying the outside steps and go straight to the innies. square root 3 times square root 7 is going to be positive square root of 21. And then the square root of 3 times the negative square root of 3 will be the negative square root of 9. Okay, 49 we know squares out to 7. Negative 21 plus positive 21, those two things cancel out. And the square root of 9 is, the square root is 3. So 7 minus 3, well, that is 4. So now we have 2 square root 7 minus 2 square root 3. So remember when I said when you multiply an expression by its conjugate, you'll wind up with a whole rational number? Do you see how that happened? We had 2 perfect squares, and then we had 2 radicals that canceled each other out. So from all that mess, we got 4. It's pretty cool. So anyways, here we are. 2 square root of 7 minus 2 square root of 3 divided by 4. We can reduce this, right? 2/4 is 1/2. So we've got 1 square root 7 divided by 2 minus 2/4 is 1/2. 1 square root 3 divided by 2. And if you wanted to, you could put them all on the same line as 1 square root 7 minus 1 square root 3, all divided by 2. Either way works, but that's our final answer. And as you can see, we've done our job because there is no irrational denominator anywhere in sight. Okay, guys, that's it. I hope this was clear. If not, pause it, rewind it, watch it again. Make sure you write down all the questions that you have so that we can talk about it in class, and we will go from there. Great job, you guys.